Hi, so in this lecture, we're going to try and compute the potential due to a ring. So here's a ring, and this ring has a radius r, and it's lying in the plane, which we call the xy plane, and it's uniformly charged. So the total charge divided by the whole circumference of the circle is the line charge density of this ring. And the question now we want to solve, find an exact answer to is what is the potential generated by this ring? Okay, so how do we start? Well, obviously, away from the ring, there's no charge, so the potential has to satisfy the Laplace equation. But given the geometric nature of this problem, it's probably advisable to try and solve this problem in the specialized coordinates, which is the spherical coordinates, having three variables r, theta, and phi. And in particular, theta is the angle from the North Pole, or the z-axis in this case, also known as the polar angle. And phi is the angle measured from the x-axis. But however, since this ring has a certain symmetry, and this symmetry has to do with the independence of the shape of the ring after you have rotated the ring by a certain angle about the z-axis, and that leads to the elimination of any phi dependence in the potential. So instead of this potential depending on three variables, it will most likely depend on only two variables, and that does simplify the problem a lot. Okay, so invoking the symmetry from the early stage of the problem solving is always a good idea in physics. And here is one example of that. So, so this is the Laplace equation, but written out in the spherical coordinates. And we haven't really talked about how to derive the Laplace equation or how to express the Laplacian in spherical coordinates. That was actually covered in chapter 1 of this book. But I have skipped that for the reason that those of you who are in this class are supposed to have had familiarity with that subject. And and I still maintain that position, but just as a insurance policy, I want to make sure that you are aware of this math. So I'm going to give you a homework. The homework problem is for you to go through the derivations of this form of the Laplacian. Okay, so your summary this week has not only to include the summary of the lecture, but also the solution to the question, how to derive this Laplace equation in the spherical coordinates form. Okay, but I'm just going to proceed on the assumption that you already know how to write this down, and I'm going to just focus on solving it. So this is a partial differential equation consisting of two variables. And since the only technique that I know, and pretty much everybody in the world knows, in solving such problem is the separation of variables. So I'm going to adopt that ansatz and express my potential as a product of two parts. The r part depends only on the variable r, and the theta part depends only on the variable theta. Okay, with this substitution, now this Laplacian becomes this. Certain functions move outside the differential because it does not depend on the variable for which differentiation is taking place, which is the key feature of the separation of variables technique. And by further dividing this thing by the product of theta and r, we have this expression. And you can immediately recognize that this part only depends on the variable r, and this part depends only on the variable theta. So according to the standard approach in solving partial differential equations, we can say that this part must equal some constant. I'm going to call it k. And by necessity, then this part must be equal to minus k. That means that the r part of the solution obeys this ordinary differential equation, while the theta part of the solution depends on this other ordinary differential equation. We don't know how to solve them yet, but at least it's nice to know that the partial differential equation problem has been reduced to a pair of ordinary differential equations where we have at least some hope of solving and finding the solution. Okay, so let's first focus on the r part of the problem. Since we don't know any better, I'm just going to pretend that the solution is this polynomial form. If this was the solution, then this r squared r prime equals that, and then for the further derivative of that will be this. And now that equals the k times r over here. Now that will only be the case if k was equal to m times m plus 1. Okay, so k now has some constraints, or at least has some connection to the exponent that shows up in the solution. And now the same m makes an appearance in the theta part of the equation, like that. Okay, so you probably won't recognize this differential equation very well. Not because you haven't studied this, but because this is not the way we normally write this equation. We write this equation in a different way by choosing a different variable. Instead of working with angle theta, we work with the cosine of the angle. Let's call it A. Then this differential forms change from d theta to this. And then this form becomes, after a couple of manipulations, becomes this. Okay, so if you're not already familiar with this kind of math, it's really necessary that you do go through all the intermediate steps by yourself. These are pretty straightforward calculations after all. And after those exercises, we arrive at a slightly modified version of the equation, which is satisfied by the angular function theta. Okay, so this is not exactly the most friendly looking equation you have, but actually this is a pretty famous one. Actually, this is one of the most famous second order differential equations that was ever discovered. And this is called the Legendre equation. named after some French mathematician. And here's a tip: if you have problem remembering this guy's name, Legendre, and the equation named after him, just remember that this equation arises whenever you try to solve the Laplace equation in the spherical coordinates. Okay, so the Laplace equation can be solved either in the rectangular coordinates, or in the cylindrical coordinates, or in the spherical coordinates. Those are the three coordinate systems that most often appears in the solution of the Laplace equation. And whenever you try to solve the problem in the spherical coordinates, then this guy always appears. There's no way to avoid running into this equation, and therefore its solution, called the Legendre polynomial, are also a must. They make a necessary appearance in the solution of the Legendre of the Laplace equation when you try to solve it in the spherical coordinates. Okay, so I'm spending a lot of time telling this because I learned about solving this Legendre equation more than 30 years ago, but for some time I had trouble just remembering where have I seen this equation. So what happened was I just knew the technique for solving this equation, but I forgot the context in which this equation arose. And then it took me a little while to figure out that this was a natural consequence of trying to solve the Laplace equation in the spherical coordinate. So then that gave kind of a physical context to this whole endeavor of writing down the Legendre equation and also to solve the solution of it. Okay, so I hope you remember not only the solution, but also the context in which this solution is taking place. Okay, just another reminder, I said that K should be expressed as m times n plus 1, but this is also equal to the case where m is replaced by minus m minus 1. Okay, so what that means is that if r to the mth power is the solution, then this guy is also the solution. So they're both solutions, and the general solution must contain both contributions as a linear combination like this. Okay, and then the angular part contains this p, which is called the Legendre polynomial. Okay, so explicitly, the zeroth order Legendre polynomial is 1. The first order polynomial is cosine theta, and the second order Legendre polynomial is this thing. So there's some math that goes into the derivation of all these expressions, and also you have to worry about the normalization factor and so on. But since all of those things are documented both in this textbook and in any textbook on mathematical physics, you can just refer to them the same way that you refer to Wikipedia or some form of encyclopedia for well-documented knowledge. Okay, so we have found a pretty general form of the solution to the Laplace equation in the spherical coordinates when there is a rotational symmetry such that the azimuthal angle phi should not appear in the solution. And under those assumptions, this is the most general form of the Laplace equation. However, you can see this equation has a problem because this first term, r to the m, obviously diverges when the r goes to infinity, whereas the second term obviously diverges when r goes to 0. So it doesn't make sense to try to keep both a and b in the same solution because one of them is bound to give you a problem because they diverge. At least one of them has to diverge, and we don't want divergent solutions because they are not physical. So what do we do about it? Well, what we do about it is to introduce a kind of a cutoff. So let me call this cutoff big R. And then we claim that for R less than big R, then I will only choose this part, which contains no divergent solutions. And for R greater than the cutoff radius R, we choose this form, which also has no divergence. Okay, so what we do is we divide up the space into two parts, and within each part, we only pick those solutions that have no divergence whatsoever. Now, however, across little r equal to big R, these two solutions have to join together in a continuous way. And the only way that continuity can be guaranteed is if we require that, this little r should have been a big R. These coefficients match order by order for every m. Now, there's a pretty convenient way to ensure that this always happens. Instead of writing r to the m power, I write r over big R to the mth power. And I do the same thing here. And then I use the same coefficient am in both of these regions. So this way you can see that when little r equals big R, these two expressions become identical, and therefore you have a continuity of the potential across that particular cutoff radius. Okay, now we have only one job left to do. That is to solve for the coefficients am. And of course, this am depends on the particular nature of the problem. And here the nature of the problem that we have to deal with now is coming from this ring that has a radius big R. Okay, so that's the sort of boundary conditions that has to be satisfied by carefully choosing this coefficients am. Okay, so the way to think about this is you can imagine this sphere whose radius is big R to be separating the region inside from the region outside. And this sphere is charged. And because of the charges that are sitting on the surface of the sphere, you expect some discontinuity of the electric field as you go from inside of the sphere to the outside. Just remember the case of an infinitely large charged plate. And you see, we saw that there is a discontinuity of the electric field as you cross from one side of the plate to the other. And that same thing happens whenever you cross a surface full of charge. So again, the boundary condition would be that this electric field in the radial direction just outside that sphere minus the electric field at the radius just inside that sphere equals the surface charge density divided by the dielectric constant. Okay, so both of these expressions can be worked out quite easily since we have these expressions for the potentials both inside and outside. And then so this difference is equal to that expression, as you can no doubt guarantee for yourself with only a short amount of calculation. Okay, so this is some infinite sum of the Legendre polynomials. And that infinite sum has to somehow reproduce this charge density function on the right-hand side. But okay, so now we have one final challenge, which is to choose this form of the charge density appropriately for a ring-like charge density profile. Okay, by ring-like, what I mean is that charge density is confined to the angle equal to theta over 2, pi over 2, sorry, along the equator. Okay, so the only place where there is charge is where cosine theta is equal to 0. Okay, furthermore, if you integrate this charge density over the surface of the sphere by introducing this volume element of the sphere, area element of the sphere, then the result better be equal to the total charge, Q. Okay, so the only way to choose the charge density function in such a way that both of these requirements are satisfied is if you choose it as a delta function. Okay, so so this turns out to be the right way to write down this charge density function. And the problem reduces to equating this left-hand side, which is an infinite sum of the various Legendre polynomials, to match the delta function on the right-hand side. Okay, again, the final task of solving for these coefficients AM is left as a homework exercise, because this again refers back to your background in mathematical physics and the theory of special functions, which are necessary mathematical backgrounds to study the electrostatics. But again, I want to assume certain level of familiarity with those subjects from the students, and I want to check that you do have those backgrounds with you. So this is a homework problem that should accompany your summary. Okay.